I'm Scaglione, a professor in electrical, computer, and energy engineering at Arizona State University. And Anna has very broad scope of interest. So her research spans across many disciplines in signal processing, communication networks, control, and power systems. And within power systems, her research focus is in network protocols for intelligent and secure energy delivery systems. And today we will hear about demand dispatch schemes and how we can connect these schemes with current market practice and what problems will occur with this. So.
Thank you. Thank you for the introduction. So our previous discussion with the speaker was very helpful. I think I will sail through my talk because a lot of the discussion I think clarified a lot of the problems. And it has been also mentioned before that renewable energy comes with zero marginal cost, but unfortunately the issue is the non-coincident peaks between demand and supply of energy. And so we always observe that as we insert more renewables, the system becomes more expensive, and the population that doesn't know why is baffled why we know exactly why that happens. And so demand response is very important to essentially cure this problem, cure this non-coincident peaks issue, and then rely on fewer and fewer reserves that are fossil fuel based. So everybody pretty much understands this problem. So what kind of flexibility can we harness? So I'm going to focus on mostly residential loads. Buildings would be part of that, but not large industrial loads. And there are basically three categories of loads, like resistive loads, which are lighting. Essentially, you can shed it, you can dim it, but it has to be used sparingly. It's mostly controlling lights is mostly for energy savings, not really for controlling non-coincident peaks. The ones we are really after are thermostatically controlled loads, and these can be, their consumption can be shifted typically in shorter periods, sub-hourly periods, and they also can be shifted more dramatically if the customer is willing to sacrifice for comfort. And deferrable loads, which can be interruptible or non-interruptible, and these typically have longer duration and can be deferred by hours. So, okay, so the objective of this talk is twofold. As the previous speaker acknowledged, there are millions of control knobs that we will have to manage, right? So that we need a management framework that could control of these devices, and we need to modify, more importantly, and that's what the discussion was about, the retail and wholesale market in some way so that it can accommodate for this capability of controlling all these loads. So the aggregator, as was explained before, is sort of an interface. It's the archetype for this interface that exists between the retail and the wholesale market. And there are a number of load control models. It's a little bit like Warren Powell was saying, it's a little bit of a jungle also in the field of demand response. But there are some basic old ideas that have led to new incarnations, and I will try to connect in this talk how these old ideas led to new ideas. And I will put around comments on what I think is good and what is bad and what is ugly, and the disclaimer is this is entirely subjective. I just don't want to make this talk too boring. Hopefully listening to me saying that something is ugly will wake you up. So flexible demand management. So the aggregator interface has to essentially manage and control this large population of appliances and also somehow convince the customers that that's a good deal. And then it has to reconcile what it can do and what's economic to do with the wholesale market, where it may have to purchase or essentially buy and purchase energy, but it may also have to profit out of the effort it makes to control the consumers and package whatever it can control to the market in some form of bids. And so there has been a lot of research in both sides, And a little bit of an issue with some of these research is sometimes it's generally focused on the retail side or the wholesale side, and the two are not very well reconciled. So notice that the aggregator, as I said, is kind of the symbol. It doesn't have to be necessarily an entity. It could be a distributed algorithm, and everybody sort of shares the benefit. And there is a lot of current hype about blockchain. I will touch upon it just right in my conclusions, because essentially the idea is to replace a middleman and with a distributed ledger that will handle these markets in a completely distributed fashion. So the aggregator retail side, so what is the right interface? So there is aggregation today. There were a lot of deployments of advanced metering infrastructures, and right now there are programs that do time of use and emergency interruptible load shedding. And these are two forms. The time of use is a completely distributed solution. The emergency interruptible load instead programs are instead at the opposite end. It's a completely direct control, and none of the two is suitable to compensate for the uncertainty of renewable power. Time of use could be compensating for the variability, but not for the uncertainty. And so dynamic pricing is the sort of holy grail that we would like to have. Some signal to the customers that there is congestion on the grid, something that we are not accustomed to. We think that it's bad to consume a lot of energy, but we don't see that the time at which we consume is important. Okay, no, I had done it. Okay, so the dynamic pricing interface. So the aggregator needs to compute an ex-ante retail price for power and communicate that to the customers, and the customer have to schedule at home what they have. It can communicate it typically to some hub, let's say an home energy management system, that has to then utilize this price to schedule the loads. Now the aggregator observes how the customer responds, then it observes it perhaps because the HAMS gives it some direct information, but also because it can meter the consumption and then can adjust the retail price to essentially make a profit or balance the system correctly. So the ideal pricing scheme, this is sort of Power Markets 101, should be attempting to maximize the social surplus. In this case, we have a lot of customers that participate. They could be even be prosumer, they could be generate some power. So what we would like to do is to calculate the perfect competitive marginal price, which will be in the simplified model, the Lagrange multiplier of the balance constraint. And obviously this is great because if we get the price right, everyone will contribute to maximize social surplus and will choose the optimum point. But the problem is, the sticky point is that we come from a culture of load inflexibility, and so right now figuring out how to use all the intelligence and computation and communication power that we have and knowledge that we have about people and behavior to characterize, however, the utility of consumption is still a difficult problem. And if we don't get that right, then we can just take incorrect decisions and obviously cause all kinds of instabilities. So I would say that one of the missing point is one of the points that the previous speaker, Juan Miguel, was clarifying. We somehow need to interface and have a model that represents this object in the wholesale market, because we cannot just look at an algorithm that would perhaps attempt to balance a distribution feeder, considering that the grid will compensate for whatever mistake we make as a battery, as an infinite battery will provide for the power that we are missing or that we are producing in excess. So the wholesale market needs to accept bids, essentially, and this will be the short or medium-term solution. I don't think the solution will be immediately that everything is a blockchain. So in the short or medium term, we will have to formulate a bidding strategy for this aggregator. The aggregator could be a decentralized algorithm, but it needs to interface to a higher level of the hierarchy. And then it will need to manage with some control framework the load that is scheduled. So obey the schedule. So let's go into load control models and start from the history of distributed models. And again, this is by no means a comprehensive review, but I'm trying to sort of pick the key contenders here. So the idea of control, one of the first ideas was the one proposed by Schweppe in '79, which was to do distributed frequency control. In essence, this was completely local control. You measure the local frequency, and it is assumed that you have the ability with your load to modulate also the frequency, to respond to frequency, and so you can react accordingly, sort of doing what generators do. They try to respond to frequency. And this old idea now could be implemented by the most modern refrigerators, right? The refrigerators that we all like, that are quiet, they are actually responding to frequency, so they will be a perfect candidate to respond to implement this algorithm. Now, the beauty of these algorithms is that they require no telemetry. They are completely making the system self-healing in principle, and there has been a lot of more recent set of studies on this and really nice mathematics thrown at this problem, because the stability of this distributed control scheme is non-trivial. But there are not completely nice aspects of this. These nonlinear dynamics are messy, so the math is pretty, but if something is wrong in the math, things can be awfully wrong. And the ugly part is that the economics seems a little bit risky. Is it true? It is true that you can assign a utility, and some of these papers did assign a utility to a certain frequency. But the problem is that I wouldn't want to have a market with no telemetry, no digital trace, nothing recorded at all. Everything is local. How would we know that people are not doing strange stuff? So I wouldn't think, and I don't think anybody seriously thinks that can be an actual market. Though obviously a utility could express some local cost. It could be a control scheme. And another note on telemetry is that telemetry is not just the utilities putting advanced metering infrastructure. It's us buying all these electronic gadgets, the Internet of Things. I have a bunch of this stuff in my home. Everything is automated. I can control my lighting and have a tropical sunset lighting instead of having the lighting to reflect and read. This is already happening at the expenses of the customers, and the reason why internet companies are subsidizing it is because they're after us. They're after the information that they can gather through these gadgets. So more of this is going to come, and a lot of the infrastructure is going to be made available through all kinds of mechanisms other than the utility or the aggregator having to invest in this. So I think we shouldn't worry too much about telemetry and computation. But we do need to have a framework, and at the level of control of the aggregator and all these millions of devices, one of the first ideas that has been combined and looked at in conjunction with this distributed algorithm is the idea of network utility maximization. Essentially, you want to utilize the aggregator as the broker that will pass prices but enforce the balance in this grid, and then you can use the dual decomposition to just easily come up with all kinds of different formulations of the problem. And the industry sort of married an idea, but sort of made a version of this idea, which is the version I would say that a baby will make with a crayon, right? A little drawing version of that is ultra simplified. The idea was that they wanted to utilize the AMI meters to pass a price to the home energy management system, and there is nothing wrong with that. But the standard that they wanted to pass was the idea that they will meter and establish a baseline for the customer prior to engaging the customer into the dynamic pricing program, and then after that they will be paid at LMP for the megawatts that they consume relative to that particular baseline. There is nothing like a baseline or megawatts in the notion of network utility maximization. So this part of the problem is really strange, like that you're compensated for not consuming what you should have consumed. It doesn't really make economic sense. And so actually it's not that strange that it was actually that even though FERC was promoting this idea, the DC Circuit Court said that this was illegal, and so this didn't happen, right? So if we're thinking about regulations, it was trying to promote it, this regulation was trying to promote it, but the implementation of the idea at least seemed to be flawed. And so baseline megawatts, these are the ugly parts of this. But obviously, the literature, yes? What is this? This is a problem of shadow. Okay. Yes. So there is another problem with this. The other problem is that the US is a retail monopoly. And so this would be a horrible idea, right? So if there is a monopolistic retailer that is giving you a price, they said that they will give you the LMP, but who knows? He knows exactly what you're doing and what you want. Why would the monopolistic retailer not utilize this power to just overcharge you, right? I mean, this is not compatible with the monopoly. So that would be a really good reason to anonymize AMI readers if you were in a retail monopoly, because at that point, obviously, you are totally in the hands of the monopolistic retailer. But the original idea of network utility maximization is not a bad idea, and a lot of the papers in the literature have tried to propose different schemes, and a lot of the variations are just looking at different ways of characterizing the flexibility of loads. And one that is relaxing very much the constraints of the load says that basically if a load would require a certain energy, and it does require it by a deadline, any load profile that is compatible with that is what's feasible by the customer. And this is a very simplified model that would make the feasible region bigger than it actually is, because, for instance, non-interruptible load will not behave like that, right? You will not be able to interrupt it with this way. Other ideas that have been circulated say that you have an instantaneous utility that describes your value for the load that you have, and then somehow there are diminishing returns. You are not going to consume more power. So eventually, most people are converging towards the idea that there is essentially, for different classes of loads, there is a feasible region. Now, this feasible region can change depending on parameters. For instance, for your thermostat, your deadband, if it's very narrow around the value, you are perhaps more comfortable. If you make it wider, you're perhaps a little bit less comfortable. So this feasible region is a function of choices by the customers. But outside this feasible region, essentially, you have zero utility from the consumption. So you want to characterize it as such. And then you can simplify by saying that there is, one of these feasible regions that are chosen by the customers, and then you have to respect this feasible region and have fixed utility. And the inconvenience of that model, even if it's not realistic, is it typically comes with integer constraints, which makes the problem non-smooth, and so makes the network utility maximization problem a little bit more problematic. So, but let me say that the typical objective then of the aggregator can be formulated as trying to minimize the real-time cost. The aggregator has somehow offered in the market, or tried to clear in the market, a certain profile that should serve this load, and any deviation from this will have to be cleared in the real-time market, so it can penalize deviation, up deviation and down deviation from this load. And then with the dual decomposition again, all the customers could just take the price that is calculated by the aggregator and submit the demand profile, and then they can iterate until they converge to the optimum schedule. And so this is a lot of work that essentially goes in this direction. You don't have to minimize, you don't have to reveal individual constraints. Obviously, this algorithm will have to run ahead of time, and then it's all completely decentralized. So this would work very well. But what is the issue with this? There are some issues. So if you can see in these curves, we have these coordinated hams that on the right side that reschedule with the red profile the load that otherwise would have followed the blue profile, and the dashed line is what the aggregator is trying to, is the aggregator profile, desired profile, right? So you can see that the deviation is not that big. The left side instead shows what will happen if there was sort of a myopic reaction to a price from the side of the aggregator. So if you don't consider the constraints that are in the system, you really don't do a very good job at matching the profile. But there are bad and ugly aspects of this, and one bad aspect is that the integrality constraint leaves some duality gap. So if you have these appliances that switch on and off, right, they will give you an integer constraint, and that makes the problem not converge to exact optimum. And there is also this other ugly aspect, is that it's not that easy to understand what is that you can accomplish ex ante from the aggregator point of view, because you don't have knowledge of the utilities, you don't have knowledge of the constraint, so you have to somehow learn the behavior, and you have to learn what would be feasible when you implement your distributed control algorithm. And so that's a little bit of a pitfall of thinking distributed but not thinking that you will have to somehow package this for the aggregator. And so then we go the opposite direction, right? So the centralized schemes that know everything and control everything and therefore are extremely reliable. And they essentially have they are the research version or counterpart of what are the direct control schemes that are used for emergency interruption of loads, right? So you do selective load shading or thermostatically controlled loads, and the typical way this is done is by imposing a certain duty cycle and saying that the device should not be on more than a certain percentage of time during the period. And the idea is very simple. Basically, you have here a histogram of the different duty cycles across the population of a certain set of TCLs. And if you can push the mass of the distribution towards lower duty cycles, then you are going to have lower energy. So you can control through the average of this distribution, you can control essentially the load profile. And you get accuracy out of the law of large numbers. So this has very simple telemetry. You just broadcast a signal and you say this percentage of you, flip a coin with this bias, you should have this duty cycle, and so on and so forth. Now the bad part here are the economics. There is no regard to discomfort at all. And the ugly part is the rebound peak. This is, it's controlled like there is no tomorrow. So the air conditioners are doing things now, and then obviously afterwards, after the control period has ended, they will come back and try to set the house at the desired temperature, and this will create problems. But this gave rise to interest in creating load models, aggregate load models, and the first bottom-up load model was proposed by Chong and Malami in '84, and what they did is essentially they said, well, if you look at the individual model, you can actually kind of lift up this model into a population model and understand what are the dynamics of the particular histogram that I was showing, how will they evolve as a function of the temperature. And what they are after were differential equations that will express the dynamics for the average probability of a TCL to be on at a certain time. And they found a nice formulation that involves the solution of partial differential equations. So it's not really a control scheme, but they actually kind of paved the way to think about how to construct load models that were based on the physics of the individual devices. So it wasn't really a control strategy, but fast forward, this work was picked up, and here I'm citing one of the papers that sort of refined this model in particular. So the idea was, well, why don't we utilize this histogram as a signature, a dynamical model that describes the entire population? So we are going to bin the temperature and essentially track the dynamics of the load signal that we see in aggregate from this population by mapping them back into the histogram of the population in the temperature bins. So these are all these normalized temperature bins. And then we have to discriminate between those that are on and those that are off. So there is a certain percentage that are on at that temperature and a certain percentage that are off at that temperature. And what the control does is essentially pushes them to be off or to be on. So it's modifying the state, and that can be represented with a simple classic linear dynamic with control model. So this is really nice. This shows that you don't have to have rebound peak. You can keep everybody in their deadband. Now, the bad is that the economics are a little bit unclear. This was not proposed as an economic model. It was proposed as a direct control model. This, though, may not be energy neutral because you're turning things on, turning things off. So even though the customer is kept in the deadband, if you charge them on energy, you made them consume more energy. It's not clear that they should be willing to do that. And also, here the users don't choose anything. And so users typically get upset if you say, oh, I'm going to control your thermostat. They would be happier if you gave them the option. The one thing that is a little bit impractical about this model is that it does assume homogeneity for the entire population, but this is actually me being a little bit petty because you could cluster these in different population and apply it a little bit different with more complexity. So the main point of this work was that it really tried to look at these population models as a mean to describe accurately what is happening to the load at the aggregate level. And some of these populations, if you look at them this way, they actually lend themselves with no binning, no approximation to be controlled quite easily. So there is a number of work that noticed the similarity between the need of scheduling charging of electric vehicles with a deadline and the need of scheduling processes on a processor with deadlines, right? And so in this case, all you have to keep is essentially a policy for the stack of the cars that have priority, and the priority can be based on simple processor time allocation policies like earliest deadline first or least lasting first, and there are all kinds of nice results that show that under certain conditions these policies are optimum and will lead to the schedule that is economically most advantageous. So it exploits the flexibility that is available in the system in the best possible fashion. Okay, so the good of aggregate models is that the most important inference is that now you have control, right? So you know what is going on. You can see what this aggregate model does. So you have a description, and this description actually in this case is explicit. It's not an optimization that you have to solve. You have, because here there is no market, it's purely control, is a complete description of what you can do. And many have argued that one natural way of doing it is, well, if we can use the battery model for a single load, why don't we use the battery model for the entire population, right? Why don't we say the flexible demand is like a giant battery where essentially what the customer wants is just energy, so you fill this battery tank with energy that you want, and then eventually you have to deplete it because you have to serve everybody. And so these models were actually used for a while to assess what demand response will do in the market. And so one part of the objective of this talk is also trying to see whether this is a good idea and how good an idea this is. But the reality is that the feasible set for an aggregate load, it amounts to an operation which is unfortunately dauntingly complicated if you don't do it, if you don't handle it with care, is really a Minkowski sum. So what you're trying to find when you are trying to aggregate a population model is you have load 1 has a certain feasible region lambda 1, and load 2 that has a certain feasible region lambda 2. And what you're trying to construct is that set, which is not a sum of sets, is really the Minkowski sum of these sets that contains all the possible profile of the sum of two loads that are in the Cartesian product of that set. So that's really what one needs to do. And in general, this is a complicated operation. So what most people have done is they have used this idea of clustering, so building a template, and then from that template, essentially constructing directly the Minkowski sum rather than doing it systematically one by one. And so what I'm writing here is sort of this template summed n times, right? This operation that seems to be equally complicated, actually, we can do just out of serendipity. We can actually see how to do it. But there is a trick that the way we choose the template really affects the result, how explicit this result eventually is. Okay, let me go ahead. Okay, so let me clarify this with an example. So suppose that you have a simple load, which is a battery, has a certain initial charge. It arrives in the system, it's plugged in at time TIA, and it can be charged up to a certain point. So the feasible set is the set that we have up there, this Li. And now we want to aggregate it. So let me just utilize this partial x to denote finite time difference. So my expression are a little shorter. And then the important variable here, the real control variable, is the way we shift population from one state to another state. And that is indicated by the partial dx x prime. X is the origin state, x prime is where I put it, right? And I'm moving mass of population from one place to the other. And so for this battery model, it's not difficult to show that you still have an integrality constraint, so you can have to move integer number of batteries. The total number that you can move cannot exceed the population that you had originally, right? And this would be this constraint. But essentially you can also, everything is normalized here, you can also, and the rate of this charging and discharging is arbitrary, you can, it's not difficult to see that the load profile that you get is in a linear relationship with this control signal, this partial dx x prime, that leads to the Minkowski sum of all these batteries, which have nothing else in common other than being batteries and having an arbitrary rate of charge. And so you can see that there is a state that I need to track in order to understand what's feasible at time t. So in fact, this is not completely correct. This is giving me a feasible region that has intertemporal constraints, and the intertemporal constraints are a function of the dynamics of the number of, in this case, batteries I have at a certain level of charge, and the dynamics here are depend on the exogenous arrival of new batteries that plug in, and on what I'm doing to control them, okay? And so the other thing that I put there in blue is that that's stochastic. So what's feasible to me is random, because the arrival of these batteries, these customers arrive at random. So I can generalize this, and I have now a bunch of equations. I don't want to go in detail because otherwise you really are going to fall asleep. But I want to give you the gist of it, right? So for electric vehicles, we need a little bit more complicated problem, more complicated model, because first of all, we will have a fixed rate of charge, and also we have deadlines. So we not only have a time of arrival, but now I have a deadline, and that is the characteristic that is a consumer decision, right? And so the state that I want to utilize is not anymore simply state of charge, but it has two variables. One is the residual time that I need to charge, and the other one is the slack time, how much time I've left relative to the deadline. And so you can actually just encode all of this information in similar constraints, and you again can by hand do the Minkowski sum, just thinking about what will happen if you now again bin the population based on in which state they are, what residual time and slack time they have left. And this prescribes these nasty looking set of equations, but however, equations that are all linear constraints, so they are actually not that just define a linear convex region for the load. And you are quantizing in the sense that you are don't arrive with a state of charge which is a discrete value or a slack time which is a discrete value, but of course if you quantize finely enough, you can contain the error that you make in representing what is actually going on. And the interesting thing is that you can do this also for non-interruptible appliances. In this case, the state of the appliance, the individual appliance, contains both the on or off, so idle or on state, as well as the deadline. So if you want to write the constraints that you have for the individual, the important cute fact is that you can write the load profile again as a linear mapping, but in this case it's a convolution of whatever is the template of the load profile for the non-interruptible load, and essentially the delta function that signals the fact that you turned on that. And if you do that, then you can have an aggregate description which has a convolution of all of these signals. Again, these are the control signals, how much population we shift from one place to the other, and everything else is a linear constraint except the integrality constraint, which for a very large population we are going to systematically neglect and just relax as being possibly a real number. Now for the TCL model, as I said, most people that looked at aggregate model followed Chong lead and utilized this particular model that utilized the hybrid state, the state of the temperature essentially and the on and off state to be in the population. The only slight problem is that TCLs are, the ones that you would go and think these are the easiest to model, but in fact they are a little bit nasty. And in particular, what is nasty about this is that you remain with an implicit dependency with the temperature, which is also the reason why you want this to be homogeneous population with all with the same temperature, all with the same parameters, and so on and so forth. So this is not that nice. So after quite a bit of work, we reached the model which actually removes this issue. This model is quantizing based on the energy loss, so it's looking at the thermal battery essentially as a thermal battery. I'm not going to omit the details because there are too many equations that are not very informative, but the important thing is that if you do that, and that's just to showcase the fact that the template you use to do these Minkowski sums matters, you actually obtain a linear affine relationship in the outdoor temperature. And that's an important parameter because the outdoor temperature is what causes the stochasticity and all of these population to fluctuate together towards a certain behavior. So this opens the door to simplify the introduction of these models into stochastic optimization, in particular to tie the flexibility of these models to not only stochastic but also variable temperature profiles. And so in the end, out of all these models, not just the TCL, what you get is a set of regions, right, that define all these linear constraints that I was mentioning. They define certain regions, and these regions vary based on these random parameters. In case of the TCL, it would be because of the outdoor temperature. And if you have stochasticity, these are two periods, the loading period 1 and the loading period 2. Those are the feasible regions that correspond to different outdoor temperatures. If you have to bid in the market and you have to provide a range in which you can change your load, you have to find that box that fits in all of these regions, essentially. And then by passing that information, then you can obviously offer yourself as a reserve capacity and can be scheduled in the market. So that's a gist of the idea, right? So if the aggregator has this knowledge, it can perfectly bid and also cope with the uncertainty that it has on these parameters. So how do we characterize this feasible region? I made the drawing. How does the drawing look? Actually, there is a better way of looking at this over time, and it is not looking directly at load. Like here, I have those three policies, right? The red, the tiny dot blue and the dashed blue, right? And they seem to not be in any relative position. While in the curve on the right, the tiny dots is in the middle and the other two are at the edges, right? And I can actually tell you that these are the two ways of looking at all these policies over time that tell you where all the policy lies. They actually lie all inside this region. And what is this region? Okay, so there are two extreme policies, and here I'll illustrate it for the EVs because it's the most obvious case. One is that I charge everything as fast as I can, as soon as they come. That's the energy first policy. And the other one is that I am the slacker. I just wait as long as I can to do everything. And these two extreme policies provide the two extreme values for those particular function of times, what I call the energy state and the slack state. And they are just counting how many, sort of the average, the average number that you get that has a certain particular slack, and in that case it has a certain particular residual time times charge, so it's the amount of energy you have left to charge. So anything that you do will be always lying in the middle of this, right? So that's the right way of looking at what's feasible. And it's not way of looking at intertemporal constraints between loads, because you can see there that you don't see any particular intertemporal constraints between these different trajectories, while you can see that that's the envelope of the trajectories right there. Now, why are these going down? Because there are no new arrivals here. So I'm assuming I have a certain amount, and all I'm doing is depleting them, right? But as I said, in case of EVs, you have new EVs that plug in. So you have a model, you have a dynamical model, and if you have a probabilistic model for arrivals, for instance, you have a non-homogeneous Poisson model for the arrivals of these cars, then you can actually project further in time. You don't have something dying, this battery is replenished, and you can always see over time what is the region for the energy state, right, between the two extreme policies, if you continue to apply the two extreme policies. And you can say it with a certain quantile, so you have a probabilistic description, essentially, of your resource and what's possible. So that's another way of visualizing, which is more effective than looking at P-min, P-max type of constraint, or how the load intertemporal constraints are related. And so, since now we have this model that ties directly aggregate TCL consumptions with temperature, we utilize it to disaggregate CAISO data. Admittedly, the parameters that we are utilizing for the thermostats, their typical ranges, the typical HVACs that are available in California are very coarse. They're based on a survey. So this was not supposed to provide very accurate disaggregation, but we can formulate a simple regression problem where we take the CAISO load and we assume that the baseline that is not thermostatically controlled loads is as a constant average, and so therefore we try to find those layers of the cake that correspond to the different clusters of different type of HVACs in the system. Again, very coarse, but actually it does work pretty well. So what we utilize is the temperature profiles from NOAA. Our model extract what are the plausible contributions from the thermostatically controlled loads, and now we can reason. We can essentially say if all of these thermostatically controlled loads that we think are in the system were to be used as reserves, what could we do, right? And actually the results are really interesting. We can increase or decrease the load by multiple gigawatts for over 90 minutes. So in this chart what you see is the color tells you how much time, and here is how much you spin up or down, right? So yellow, it's long time, and therefore, of course, you tend to be yellow in the middle, right, and dark outside because you are increasing the down spin or the up spin, okay? But you can see it's a lot of yellow, right? So for quite a bit of time, for 2 hours, you have quite a bit of space to alter the load, and do so with minimal discomfort for the user. You don't increase their temperature more than 1 or 2 Fahrenheit. Of course, this is highly seasonal. And then here is the ugly part of the pure curtailment mechanism. You can see in the red line that rebound event after the control period in red, which instead doesn't happen if you utilize the control policy. The control policy is in green, and you can see that it follows perfectly the load and remains on top of the load profile after the event. And this is the temperature deviation. So once again, you have huge temperature deviation with the curtailment, while if you have the control, you can control it. So what about EVs? EVs, we don't have data, but it has become a little bit standard to utilize this travel survey for residential parking to supply, mock up some realistic data. And so you have obviously a non-constant Poisson arrival rate because people come home in the afternoon after they go to work, right? So you tend to have arrivals and parking in the evening. And we assumed here that all of these vehicles are 10 kilowatt charging capacity Tesla Model S, right? And what you see there is this distribution of slack time, duration, and service time, those S and R variables that I utilize. So the green profile shows clearly 3 modes, saying that the population essentially when they park and they potentially can be plugged in, they come either with very little service time but also very little slack, or they have sort of an average slack time but they don't need to be charged, or they are much, or they need to be charged more, or vice versa, they are going to stay there overnight, and so you have plenty of slack. And just to give a sense, like this is a problem that we need to solve no matter what. Forget about demand response and being clean, because if the 26 million of automobiles in California all of a sudden are all Tesla Model S, then we will have a 40 gigawatts peak just caused by this. So something has to happen. And this probably will put people on notice that they have to control this. Whether they're going to control it this way or that way, I don't know. But something has to happen. And that's, if the entire United States went that way, it would be a huge amount. So it's not surprising, therefore, that the reserve capacity is actually quite high, and you can easily shift 50% of the base load for 3 hours. So there is a lot of flexibility there. And you can do up spin or down spin. And the other exciting part is that this is a more complicated population model than others because vehicles move. So you don't have to look at it as part of your home energy management system ecosystem. These guys are going to be in a parking lot, in a parking garage, and there is a lot of exciting work that is going on right now in providing experiments and new data. Stephen has a really nice experiment at Caltech. So this is work that I've done with one of my students. Is like, how do you model this problem? How do you model the decisions that you have to do in the transportation system and in the grid system so that people will charge rationally, they will not charge in the wrong place? So how would you design a price so that you alleviate congestion in both systems? And possibly how do you decouple these two problems so that you don't have to pass all the constraints and solve all these mega coupled system problem? And one of the key points to model this was to look at the traveling problem and the charging problem in a combined fashion through what we call an extended transportation graph, where essentially at every node where you have a charging point, we added links that consider different charging options. I'm going to charge for 2 hours at this price. I'm going to charge for 1 hour at this price. I have this flexibility, as if that is extending our travel time. So we can look at the complete utility of charging and traveling from a point A to a point B, and therefore represent what the population would choose by looking at this extended graph that combines the effect of congestion that is signaled by charging prices and queues at charging stations, and the effect of traffic on the roads. Now, I said all of these things, so we have control, we can model it really pretty. However, there is a bad aspect, right? So all of these are linear constraints, and everybody sees linear constraints. This is nice. But unfortunately, L is the load, D are your decision variable, and these aggregate load decision are tensors, you can vectorize them. They have a lot of dimensions. And so this region has a lot of little corner points, and so it's fairly complicated, right? So you don't have to ask the wholesale market to solve an optimization problem, but you give them a lot of constraints. You give them a big set of variables. So that is probably not desirable. So you want to give them a generator model, like as I said. So here you have what the generator model will tell you to do, the dispatch hour T, dispatch hour T plus 1, you have capacity, you have ramping constraints, so it looks like this green line, you give P min, P max, and maximum ramp. But how good is this model? So let me show you. This is exactly the region that you obtain for a set of thermostatically controlled loads. And the green region is what is feasible. And if you're trying to find a generator, make a generator out of this, you can discount completely the ramping constraints, obviously, because this is going the opposite direction, right? A generator is like that, and this is going the other way. This is going like this, right? So if you're trying to make, you can make a box, you don't need to make ramping constraints, right? But you also have only a tiny fraction of it. You can set this box where you want, and you will have to optimize this, just make a market bid that is effective. But you really are capturing a really tiny amount of what you could possibly do. And that's why the battery model actually makes more sense. But let me show you how the battery model fits in this feasible region. Is this perfect? It's okay, right? It's not perfect. So what is a battery model? Battery model will just add some linear constraints that say the sum of the load has to be a certain amount. So it's possible to find a region that fits within the feasible region, but is not perfect. So what I think is the good version, right? So the generator constraint being the ugly and the battery constraint being the bad. The good version will be, well, if the market can accept 5 constraints, I'll choose the constraints. Don't tell me what intertemporal constraints I have to choose, right? I will find the region that fits in my feasible region, which has a lot of corner points, but it is the best fitting region, like the one that I can optimize, that captures most of the flexibility, while at the same time being a simplification of the original market. And so we did a little study of this, and with our thermostatically controlled load models, you know, the purple is the generator, the green is the true feasible region, the red is our approximate region. And because we have temperature dependence, we can do both deterministic and stochastic optimization. And so we just look at a simple rolling horizon economic dispatch with thermostatically controlled loads that are used as a reserve. And you looked at the KAISO load that we had before. And what we're seeing is essentially what's kind of expected. Like if in the real time, if you look at the cost that you make in capacity and in reserve capacity, you decrease the cost, obviously, if you have the demand response product. But actually, if you use the constraint set, you actually do better in real-time penalties, because the full description not only is more complicated, but obviously you are taking more risk. Now, this is a very short-term result, so we don't benefit tremendously from the stochastic optimization, which also echoes some of the comments that sometimes deterministic look ahead for short periods is perfectly acceptable, and so maybe the variability, capturing the variability is good enough. So let me, I think I only have 10 minutes, right? So let me just go back to the point of dynamic pricing. Now, dynamic pricing, I said I have a control scheme. I didn't say anything about how the aggregator will convince the customers to do that. So, will this framework help me in understanding dynamic pricing? It does, because essentially what this says is that if I have a certain response to dynamic pricing signals that I receive from the aggregator, this response can only, if I have the type of appliances that are accounted in my models, this response will have something, will have a structure of this kind. It will have a portion of it which is not flexible, which I call this Li of t, and then there will be another portion, right? And in this other portion I will have all of these different clusters of appliances of different types, and what the theta parameter is what the customer chooses. It's like your deadband for the thermostat or your deadline for your car, right? So that's an unobservable part that will determine how many arrive in that category. And now, since the customer is assumed to be rational, or at least the home energy management system or the smart inverter is doing the rational choice, once the customer tells me I want this deadline, then I will choose the minimum load profile, a profile that just costs the least in that region. So really, this is a way also of essentially parameterizing what will be the response to a dynamic pricing signal. One little complication, though, that is apparent there is that we are pricing apples and oranges in the same way. We are giving one price signal. We are not telling you the dishwasher has this price signal, the electric vehicles have this price signal, this other thing has this price signal, and so therefore your reaction is actually more difficult to learn because you have a mixture, right? Because what I see, the load, what I meter, is a mixture of all of these things, right? While I will want to know your collective response, I have several different arrival processes that are function of the same signal that I have to get. So that's the parameterization for the dynamic pricing strategy, and you can utilize this to try to see whether you can learn the response. Now, this opens the door for another alternative. Can I post a price and convince the user to tell me what they actually want, what deadline they want for the car, right? So can I say that I will offer them a discount on the price if they choose a certain parameter theta for the particular load? And then in that case, oranges and apples will be priced differently. So at this point, I will have the meter will not be sufficient, right? Because I will have to essentially establish this transaction with the customer, and then I can utilize the meter to verify that actually what contractually we agreed upon is done. But the advantage of this is then I ex ante know the parameters, so I know exactly my population model. So I'm in the best position for the market because now I have complete control. I know how much I have in my virtual battery or in my feasible region to exercise. And this will actually be a very natural possible solution for electric vehicles which are mobile, so there is no need of transmitting one single price. I mean, you could actually send to a particular parking structure a price that depends on the flexibility, the charge, the amount of laxity that the car provides. And in that way, you just essentially accrue information about the population that you can utilize later to control, and also you can utilize the statistics you collect to position yourself in the market in the best way. So we did a bunch of simulations here. Again, there are much better data right now, so I don't want to spend a lot of time in that. But as you can imagine, if you were looking at residential customers, what will happen is that they will not necessarily reveal the exact deadline, right? They will perhaps be a little bit conservative. They will tell you something a little earlier because they want to make sure that their car is dead. But you can actually still harness, even if you model that, you still can harness quite a bit of flexibility, particularly at late hours of the day. So here we had some data for PHEV charging that we utilize to mock up this experiment. And with this particular data, we try to see, assuming that this program is so small that will not alter the price of the market, we took market prices from New England, right? And we had this aggregator that was choosing the optimum incentive policy for the customers to recruit them, and that was the result that I was showing before, like this was the recruitment strategy. And we try to understand what was the amount of savings that would be realized by both in total, right? And that would be essentially the consumer and aggregator saving is the pink line. The blue line is what you would have gotten if there was no aggregator and you just had done you just offered the flexibility in the market so that your profile was as low as possible. So you can see that actually the consumer plus aggregator savings is quite close to what would be the best surplus that you can get from this flexibility. But the aggregator being rational and the customer being rational leaves a big gap between what remains, what is the benefit to the customer, which is this red line. Now granted, this is not a true experiment. It's based on a model of how the EVs will respond to the market. And there are a lot of other things to say. But basically what this simple example is trying to show is that it's very likely that the lion's share of the benefits of this will go to the aggregator. And so this is essentially my last note is that this is another reason why probably people will be really responding to distributed solutions, because then they will see the actual benefits going directly in their pockets of this. And unless they see the benefits in their pockets, they're not incentivized to really change. So I hope that I convinced you that there is some kind of structure in this problem, although I have to admit that the literature is a little bit of a jungle. I really think that there is a need of a hierarchical architecture. We cannot, I mean, there is hierarchy in every problem. There is sort of geographical separation that oftentimes dictates a hierarchy. So we somehow, even if we utilize decentralized algorithms, there probably will be in layers. And so what will be the interface to the wholesale market of today could be something different, but there will be some interface somewhere to break the problem. And in any case, that interface will have to be reliable. So we need models that describe exactly what will be the response of the customers. And in my opinion, we also need an economic proposition, because otherwise nothing moves. The last note is that beside the hype, I really do think that there is a justification in all of the enthusiasm from blockchain in the energy sector. And the reason is that these will just remove the problem of the middlemen getting huge amount of the benefits out of this flexibility. And also it has other benefits. In principle, the algorithm should be verifying the validity, the consistency, and immutability of all of these transactions, which means that they should make by design the problem of tampering with economic data very difficult, so cyber attacks should be prevented. But of course, this is only speculative. It's just as good as the algorithm we put in. So it just will force the engineers that implement these algorithms to think about these three principles ahead of time before they deploy, and hopefully they will do that. But it's not a one-size-fits-all, so just the idea that you're just going to use the same algorithm as Bitcoin for this makes no sense. So what's valid, what's a valid transaction, did that physically happen, and all of these things. These are the things that are have to be tailored to this application. With this, thank you for your attention. Yes?
I was intrigued by your TCL control approach, and especially this kind of this temperature, or you say a grouping of devices and controlling them in that way. And you showed some results. I was just wondering if you could say a bit more about the actual. So that's you obviously need for kind of a hierarchical structure. So that's how you do it at a high level. But can you say a few words more about how you control them in that
yes.
case?
So basically the control is a broadcast signal where it's a randomized strategy as well. So I basically provide, I want a certain amount of population to move deterministically from point A to point B. I don't want though to tag them individually to do so. So what I give them is a certain probability of transitioning. So, and everyone flips a fair coin essentially, according to the table of probabilities, depending on the state where they are, and this induces a Markov process that leads, on average, to the desired result. But if the population is very large, the deviation is going to be small from the average. And so that's in all these aggregate models, we always say that law of large numbers will make us accurate.
In the heating and ventilating control problem that you described.
Sorry, can you say it again? I just couldn't.
In the control of the air conditioning problem you described.
Yes.
In the real-world implementation, NES set out to cool the house in advance of the need to shed load, so they had a bigger reserve capacity. Your model seems to assume that you take whatever the temperature is at the point when they...
Absolutely not.
Oh, okay.
No, I actually have the entire realms of possibility, which includes pre-cooling and doing all of these beautiful things. And I know everything that is feasible to make you happy. So if you're happy with pre-cooling, and if it's good for me, I will do it. So that's...
There is a EV charging issue which is related to that, where people's energy consumption or charging matches their journey pattern over a number of days. So typically people only charge a Tesla every 1 hour.
You are correct. And that's actually the problem.
Therefore, persuading them to charge earlier than they need to isn't just a particular arrival at home event. It also is about the possibility of persuading them to plug in and make their vehicle available to charge.
You are correct. And in fact, I'll say that that's the main error in using these travel surveys, which are not recording the plug-in events. We had some actually real data that showed precisely what you said, that people don't plug in unless they have the car fully charged. Unless they have, the car almost empty. Like we don't charge our cell phone necessarily every night and so on and so forth. However, that's a choice, right? So what I said is you have to incentivize people to give you the flexibility. If you cannot incentivize them to plug in, then you're going to get whatever they are willing to give you, right? So it's all a matter of incentives. If the program is well designed, it will have a nice reward for plugging in every time. But that's could be a parameter, one of the many parameters to make them tell you what they want.
You did that experiment, but the data hasn't yet been published.
Huh?
You did that experiment, the data hasn't yet been
But I have to say that I have some data that are not that recent that showed exactly what you said. So it was hybrid electric vehicles. And these individuals will not charge, they will not plug in the car unless the car was almost empty. And so we were looking at the travel survey and they were saying, well, okay, this is how much charge we want because they travel this much. But it was not looking like the charging events or the particular distribution that we saw on the real data, because the real data actually did show that phenomenon. You know, if you just look at travel time, you don't know if that person would have plugged in or not. So you are making an incorrect assumption on whether that load was actually available for you to charge, which is, you are overstating the flexibility. So I'm aware of that phenomenon, and I have to tell you there are some data that show exactly what you just said, and I'm glad that there are more data, but it corroborates something I've seen.
Maybe one last question.
It was more about your last observation about the aggregator caching most of the surplus. We published a paper, I think 6 years ago, where we looked at this relationship as a stackable game, and we had the same results. I mean, it makes sense. And some of the feedback we got on this work is that somehow we assume a single aggregator versus the population, but if you start having several aggregators that are in competition, they will have to work on their value proposition, and we would have to see where the equilibrium lies, right?
You're right. And also the other problem is that if they really control all these EVs, they're going to have market power.
Exactly. So I think, I agree with your observation. I think we have to push that a bit further somehow, because also some people push and show that you need specialized aggregators, so they will tend to split anyway and have some kind of nearly local monopoly. That would be the most efficient. But then we have to see where is this going to end up, you know?
Well, but then if it's distributed, then we don't care, right? So if it is a blockchain, then we don't have that problem in a way, right? Because we benefit, ideally. So somebody has to monetize all of these startups that are trying the Energy Web Consortium, provide algorithms and so on and so forth. Like they will have to monetize their algorithm. So I really don't understand this thing of distributed solution look great, but how are these companies going to monetize their R&D? That's not clear to me. They will have to do some aggregator type of role some way.
You already see that today. I think I've heard people from California saying that the business models are not viable. So maybe at some point eventually they're going to realize we cannot do that being a profit-seeking entity, and then they will, I mean, the TSOs, DSOs are just going to provide the platform and say, see, just do it, and forget about having a viable business model.
Yeah.
So I think,
And something else on blockchain, the energy you need to have the validation, the strong validation is a problem. Because if you have a small transaction, you need a lot of energy to validate this transaction.
No, okay, so that's blockchain. Blockchain is not Bitcoin. Blockchain is distributed ledger. So Bitcoin is its own algorithm, has its own pros and cons, and is trying to validate the fact that there is no double spending. This is not the same problem, right? It's not the same problem at all. So what I'm talking about is a distributed ledger which is designed to ensure validity. How do you validate? You have to have a consensus mechanism that we all agree upon and is not based on that particular algorithm.
But you believe that you have no secondary market, so the people will not change between them. So there is a centralized point that...
No, for example, let's say it's a network utility maximization problem that could be implemented in a completely distributed fashion through a smart contract. So it doesn't have to be that there is an entity that manages that. It could be just a software program that leads to the information exchange, and everybody that records what is the final schedule is agreed upon by the majority of the network. So the algorithm has to be different. It is not going to be Bitcoin.
It's not a peer-to-peer. It's not a peer-to-peer transaction.
Oh, it's not a peer-to-peer. I agree.
Okay.
No, it's not a peer-to-peer because you have to balance. It's an algorithm. It's an algorithm. It's an algorithm that does more complicated things because we have constraints.
So this question of peer-to-peer or not peer-to-peer.
It's not a peer-to-peer market.
It's very interesting. That's triggered lots of discussions. So
Thank you.
there were lots of